Hello guys, welcome to this video series on linear algebra for engineers. In our last video, we talked about the prerequisites for vector spaces, that is Cartesian products and the binary operations. So these were discussed in the last video. Today we're going to learn vector spaces and subspaces. This will be the content of today's video. Okay. So before that, let me set some notations. So R is the set of all real numbers. And script C is the set of all complex numbers. That is numbers of the form a plus iota b, where a and b both are real. Okay. Now k will denote either R or C. K will denote. So whenever I write k, it would mean either R or C. Now let's go to the vector space. So vector space is defined over k. In this course, we'll be defining vector space over k. Actually, vector space is defined over something called field, but let's not get into it. For now, we'll be defining vector space over K. So what do we mean by vector space over K? Vector space V over K. This is the question that we're going to answer in this video series. And another question would be, okay, now if K is equal to R, that is, if we're defining a vector space over the set of all real numbers, then the vector space V is said to be a real vector space. And if script k is equal to the script c, that is the set of all complex numbers, then the vector space v is said to be a complex vector space. Let's make it this color. So this is our note. Now, what is a vector space? Let's answer this question in very simple steps. So, first of all, vector space over K, we never say just vector space. Whenever we say vector space, it is always over K, over some field. And K is a field. K could be R or C. We could have another fields as well, fields which are not R or C, but we're not going to discuss them in this course. So, vector space is a vector space V over K is a set. We all know what set is. Or should I say a vector space V over K consists of a set, a binary operation, a binary operation on what? On V. And we've already discussed the binary operation in our last video. Now, there is one notation here. This binary operation is denoted by plus sign. Plus sign. Let's denote it by plus under a circle. I'll explain the reason for doing so later on. And C, a scalar multiplication. What does this mean? This means basically a function from K Cartesian product V to V. This is the meaning of a scalar multiplication. And notation is we denote this function by a dot. So what is happening is that so inside this K cross V, we have elements that look like this, where small k is from script k and small v is from vector space V, and this function takes this to k dot v. So a vector space V over K consists of a set is V, and a binary operation on V, that is a function from V cross V to V, and we denote this function by this sign plus inside a circle, And a scalar multiplication is also defined on V, which simply means a function from K cross V to V. And we denote this function by dot. Now, this is the basic structure of a vector space, but that's not how we define a vector space. There is more to it. So, a vector space V over K consists of A, B, and C such that ABC satisfies certain properties. This is a very interesting topic. Now, so what should B satisfy? What should binary operation on V satisfy? Let's call this number one. Binary operation should be commutative. And we know what a commutative binary operation is from our last video. So what this means is that for every, the symbol is for every. Let me write it clearly. For every, this means for every uv inside V, u plus V is same as V plus U. And number two, the binary operation is associative. What this means is for every UVW in V, bracketing doesn't matter. This is the meaning of associativity. What I mean is the following. If you have to combine UV and W, then you could first combine V and W and then combine the total with U, or you can first combine U with V and then combine this result with W, and you'll get the same thing. So this is same as this. This is what we mean by associativity. Okay. And the third thing is this binary operation has an identity. So we discussed that in our last video as well. So let me restate what identity is. It means that there exists. So this symbol means there exists an element in V. Now we're going to denote this element by 0. Denote this element by 0. This 0 is different from the 0 number that you know. This is just a notation such that for every V inside V, V plus 0 is same as 0 plus V equal to V. That is Adding this identity to any element in V doesn't change that element. The element V remains the same if you add 0 to it. So there is identity, there is associativity, and there is commutativity. The fourth thing is inverse elements. What do I mean by that? It means that for every V inside V, there exists an element U inside V such that V plus U is equal to identity, that is 0. This is the meaning of inverse element. And a notation is, okay, we'll discuss this notation later on. So this is the so these are the properties which B must satisfy. Now there are properties which C must satisfy. C was scalar multiplication here. The first property that C must satisfy is for every V inside V, 1 dot V is equal to V, right? So if you, what is 1? 1 is coming from, well, 1 is coming from K. And recall that K was either R or C. In R and C both, you have one, number 1, right? So this is the number 1. And if you do its scalar product with V, then you get V. That is one property. And the second property is associativity. It is slightly different from the associativity that we discussed in case of B in the following way. So for every R and S inside K, and for every V inside V, we have the following: Rs dot V equal to R dot S dot V, right? So we can shift the brackets here also. Now, note one thing. No dot in Rs, right? There is a dot in Rs dot V, and there is a dot in S dot V, and there is a dot in R dot S dot. So why is it that? Why is there no dot in Rs? Well, because Rs are both from K, right? Right? So Because R, S both come from K, and K, as we know, is either R or C. And in that case, RS means the usual multiplication. Like we have 2 times 4 equal to 8. It's the usual multiplication, right? So RS is defined. RS makes sense. It's just the usual multiplication that we're already familiar with. Now, in this case, RS belongs to K, right? And we define scalar product or scalar multiplication only for an element from K and an element from vector space V, right? So this makes sense. In this case, S is from K and V is from V. So S dot V makes sense, right? Because we defined scalar multiplication as a map or a function from K cross V to V. So we need one element from K and one element from V. Then only we can define this dot. Similarly here, S dot V is from V and R is from K. So we can define dot R dot S dot V, right? And this property says that they are equal. So Rs dot V is same as R dot S dot V. Or now there is another property which needs to be satisfied, and this property combines B and C together, right? Let's call it D. These are distribution properties. So definition of vector space is kind of lengthy, but once you get used to it, it's really easy. Distribution properties. What is that? So let's see. It means that for every Rs inside K and for every UV inside V, the following happens. Number one, R dot U plus V becomes R dot U plus R dot V. See, R dot U is inside V and R dot V is also inside V. So how do we combine two elements of V? Using the binary operation. And what is the binary operation on V? It is this plus inside a circle, right? Okay. And second thing is R plus S dot U equals R dot U plus S dot U. Now, note that on left hand side, I have used plus, and on right hand side, I have used plus inside a circle in number 2. This is because R and S are coming from script K, right? And here we can add the elements. You can add 2 with 3, to get 5. You can get 2 from 5 minus 3. You can add 2 plus iota to 3 iota to get 2 plus 4 iota, right? So here addition is defined. Here addition is defined. But in case of these, as I said earlier, this is from V and this is from V. So how do you add two elements of V? Addition is not defined there, right? But we defined it using the binary operation. And binary operation is this. So here we have to add using the binary operation. And that's why we have this symbol here. So here I am writing it as a note. So plus on left hand side is the usual addition. That's it. So this is the definition of vector spaces. So let's go over it again. So a vector space over K consists of a set V, a binary operation on V. And what is binary operation? It is a function from V cross V to V. And we are denoting this binary operation using this number plus inside a circle. And the third thing, to make a vector spaces, a scalar multiplication needs to be defined on V. What is a scalar multiplication? It is just a function from K cross V to V. And we have discussed Cartesian product in our last video. That is, what is happening is that K comma V is pair is being taken to K dot V because we are denoting this function by a dot. Now, these properties, so these things are to be related to each other using these properties. So ABC must satisfy these properties. So number one, this binary operation must be commutative and it should be associative. It should have an identity and inverse element should exist. That is, for every V, there exists a U such that V plus U equal to 0. And then there is property related to scalar multiplication. The first property is this: for every V, 1 dot V is V, then associativity, and then distribution properties, which combine B with C. Now let's discuss some terminology. So elements of V, will be calling them vectors, and elements of script K, they are called scalars. Okay. Now let's take a look at some of the consequences of this definition. So what about the inverse? So here I mentioned that inverse element exists. That is, for every V inside capital V, that is for every vector, there exists a vector such that the summation is equal to identity element 0. Now my question is, is inverse of a vector v inside v unique. That is what I'm saying is it possible? Is it possible that v has two distinct inverses? Say u and u prime. Well, the answer is no. Let's see why. So if so, suppose on the contrary, u is not same as u prime, right? That is, v has two distinct inverses, u and u prime. Since they are distinct, they are not. Now, I can write u equals to u plus 0. Why? Because we know that 0 is an identity element, and identity element can be added to any element to produce that element. So u equals to u plus 0. This is from the definition of vector spaces. Now, the 0 can be written as v plus u dash. Why? Because, well, u dash is an inverse of v. And what is the meaning of inverse? That when we add these two, we get 0. Now, using the associativity, again, this plus is the plus inside the circle because we are adding two elements of v, that is, we are adding two vectors. And how do we combine two vectors? Using the binary operation. And we were denoting that binary operation using plus inside a circle. So using the associativity, we can change the brackets. We can write it like this. By associativity, and what is u plus v? Well, u is inverse of v, so this is 0. And here we are adding identity to u prime. So what should we get? U prime. But this means that u and u prime are same, right? Okay. So that's a contradiction, right? So this is a symbol for contradiction. Therefore, an inverse inverse of vector v is unique, and therefore we're going to use the word the. So we'll say the inverse of v is so and so, whatever it is, say u. We're using the article the here instead of n because it is unique now. Inverse is unique, therefore we're using the. Note that here we're using n because here we didn't know if it's unique or not, but now we do. Now we know that it's unique, so we're going to use the. Here comes another notation. So the inverse of v, vector v, is denoted by minus. Okay, so minus v represents the inverse of v. Right now we don't know if minus v is same as minus 1 dot v or not. Are they same? We don't know. We'll see. So this is one consequence of the definition of vector space. Let's take a look at another consequences. So take 0, take scalar 0. So this 0 is scalar. So 0 dot v equal to what? So here 0 is a scalar, that is it belongs to k, and v is a vector, that is it belongs to v. So what is 0 dot? Well, it is equal to 0 dot v equals to 0 plus 0 dot v, because number 0 can be written as 0 plus 0. And now using vector space property, see this property, right? So d2 property, when we have scalars r plus s dot u, then we can write them like this. So we're going to use this property and we get this using that property by d2 property, right? We get this. And this plus is, of course, the binary operation. Now, this is inside v, this is also inside v, and every vector space element has inverse. So adding on both sides, what do we get? We get 0 dot v equals, so here we're using the binary operation plus What is this? So 0 dot v is the inverse of 0 dot v. So we should get 0 here. How about this right hand side? So we can use the associativity to write this. Again, we're adding an element to its inverse. What should we get? 0. So 0 dot v plus 0. But we know that 0 is an identity element. So it won't change this. So we should get 0 dot v. Therefore, 0 dot v is vector 0, right? That's it. So 0 dot v is equal to 0 for every vector v. Now some notation. So for vectors uv, u minus v will denote u plus minus. What is this minus v? This is nothing but the inverse of v. So instead of writing this right hand side, we'll be using the compact version on the left hand side. Now let's see some more consequences of the vector space definition. Is minus u same as minus 1 dot u? So here u is a vector. Let's see. So if I add minus 1 dot u to u, then what do I get? Well, I can write u as 1 dot u, right? Why? Because using this property of vector spaces. See this property? Look at this property. So I'm using C1 property is by C1. Now using distribution property, I can write it as 1 plus minus dot u. Note that here I'm not using plus inside a circle because this is the usual addition. So this is using the distribution property. This is by distribution property. Let me write it here, and here I write by distribution properties. And what is 1 plus 1? 1 minus 1. This is 0. And what is 0 dot u? Well, we just saw it earlier. Yeah, that it is 0. So we get 0. That is minus 1 dot u is the inverse of u. But how are we denoting the inverse of u? Using this symbol, right? So minus u is nothing but minus 1 dot u. Okay. So the answer to this question is yes. Now let's see one more consequence. So if if R is a scalar, that is R belongs to the script K, then what can we say about R dot 0? Here 0 is a vector. That is 0 is in V, right? This is the identity of V. Now we'll use the same idea as earlier. We'll write this as R dot 0 plus 0. So this plus is the plus inside circle. Again, we'll use distribution, and we'll add inverse on both sides, and that will give us R dot 0 equal to 0. This is this 0 is vector 0, right? And so get this, R dot 0 is 0. Okay. Now let's take a look at some examples of vector spaces. So first example is R2 is a vector space for R, right? What is R2? It is a set of all column vectors A comma B such that A, B are real numbers. Now, so I have said that it's a vector space. Then you should ask me, if it's a vector space, then you said that vector space consists of three things: set, binary operation, and scalar multiplication, which satisfy certain properties. And you're saying that this is a vector space. So you've given us set, but you haven't mentioned the binary operation or scalar multiplication. And I'd say that's a fair question. So let's define binary operation on this. What would be the binary operation? Well, I'm saying under matrix addition. So this is my way of giving you the binary operation. Matrix addition, or we can also say term by term addition. Addition and The usual scalar multiplication. Multiplication. What is usual scalar multiplication? Well, it means that if R belongs to R and A comma B belongs to R2, then R dot AB is just RA, RB. And what is matrix addition? Well, it means that AB and CD can be added like this: plus C, B plus D. Okay. So under these operations, R2 forms a vector space over R. You can verify all these properties will satisfy. A, B, and C. Everything will satisfy all these properties, B and C, and everything. So this is a vector space example. Similarly, R3 is a vector space, R4 is a vector space, and so on. So these vector spaces of this type Rn, these are called Euclidean spaces. Euclidean spaces. What are some other examples of vector spaces? Let me define this set. What is this set? This is the set of all 2 by 2 real matrices. So this is a vector space under vector space over what? Over R, right? It's a vector space under matrix addition. And the usual scalar multiplication. Okay. Now let's look at a known example. So let's say I define a set as equal to the set of all degree 2 real polynomials. Now, operations are, so what is the binary operation on S? Let me just write operation on S is simple addition, and scalar multiplication is the usual scalar multiplication. The usual multiplication. Question is S a vector space over R? Well, let's see. So if S is a vector space over R, then this scalar multiplication should be well defined, right? So let's take 0 from R and let's take polynomial px equal to x square from S, right? So this px is in S. Why is it in X? Because it's clearly a degree 2 polynomial, and S is the set of all degree 2 real polynomials. So it is in S. Now, what is this scalar multiplication? It's the usual multiplication, that is 0 dot x square. The usual multiplication will give 0. Now, this 0 should have been inside S, but is it inside S? No, because 0 is not a 2-degree polynomial. 0, not a 2-degree polynomial, right? So S is not a vector space with these given operations, right? Now, let's take a look at what a subspace is. So, so that V is a vector space over some field K, and K means, as we know, either R or C. So here, what we have is a set V, a binary operation, and scalar multiplication, satisfying certain properties, right? Now, suppose U is a subspace of V is also a vector space over K with the same operations, right? So its subset U is also a vector space with the same operations plus and dot. Then, then U is said to be a subspace of V. So how do we check if a subset U of a vector space V is a subspace or not? So let's see. Okay, let's go to the definition of vector space. So here we want to see if U is a vector space or not. We want to see if U is a vector space or not. And for U to be a vector space, we need these things A, B, C. So we have U, so we have set. So A is fine. We need binary operation on U. But then we said that to discuss subspaces, binary operation on U is same as binary operation on V. So we have binary operation as well. And we have scalar multiplication as well because scalar multiplication on U is just borrowed from V only, right? Now we have to check these properties B1, B2, B3, B4, C1, C2, and D distribution properties. Now, do we have to check commutativity? See, commutativity is true for every element in V, and U is inside V. So V is like parent of U. Since this property holds in parent set, it must hold in the daughter set as well. That is in the subset. It must hold in the subset as well. So we don't have to check this. It's automatically satisfied. Associativity, same. It is also satisfied because it is satisfied in the parent set. So it must be satisfied in the subset. Identity, again, now we have to check this because the identity 0 is inside V. How do we know that it is inside U? So we should check that. So this needs to be checked. Identity. And inverse element, we have to check inverse element as well. Now, associativity, again, since it satisfies in the parent set, it will be satisfied in the daughter set as well. This property will be satisfied too. And this as well. So we don't have to worry about C. We only have to worry about B, 3, 4. And what about distribution? This is also automatically satisfied. Right? This is also automatically satisfied. So we have to see only 3 and 4. Right? So let's take a note of this. if we have binary operation on V applicable on U, then we need only check or verify B3 and B4, right? That is identity. Does U have identity or not? And inverse. Does every element of U have an inverse inside U or not? That's it. Because other properties are satisfied automatically as they are satisfied in the parent space. Let's take a few examples. Example, so take V equal to R2, the Euclidean space, and U equal to this set. X plus 1 such that X belongs to R. Now, is U a subspace of V? So here, since we're talking about the subspace of V, that means we're considering the same operations that we were considering on V, right? So that is on U, we have to consider the usual addition and the usual scalar multiplication. So V is R2. What is this? A vector space over what? Over R. Remember, we were earlier using the letter K. K was either R or C. Now, is U a subspace of V? So we got the operations, usual addition and the scalar multiplication. Now we have to see if U has identity or not. Does U have identity? And does every element of U have an inverse? So let's see. So what is the identity of V? 0, 0 is the identity of V. Is the identity of V. Does U have this identity? So is 0, 0 inside U? What is the answer? No, right? 0, 0 doesn't belong here because you can see the second element is one larger than the first element. And here we have 0, 0. So U does not have identity. So U is not a subspace. U is not a subspace of R2, right? But this is not the only problem in U. U has other problems as well. For example, if I take plus 1 inside U, then binary operation should give me this, and this is 2a plus 2. Clearly 2a plus 2, this element 2a and 2a plus 2 is not inside U, right? So binary operation of R2 is not applicable on U, right? If we have binary operation on V, applicable on U, but here it is not applicable on U because it is not taking a combination of these two inside U, right? That is, we're not getting a function of this form. Okay, we're not having this kind of function here. So binary binary operation of V is not applicable on U here. So there is no binary operation either, right? Now let's take a look at another example. Again, take V equal to R2 and take U equal to X X such that X belongs to R, a real number. Is this a vector space? Well, first of all, let's see if binary operation of V is applicable on U or not. So take X X and add it to some Y Y. What do you get? X plus Y, X plus Y. This is inside U, right? Because both entries are same, X plus Y, X plus Y. So we're inside U. So yes, binary operation is applicable because we're getting a function. Okay. Now, so this part is. How about the identity? So 0, 0 is the identity of R2, is the identity, and clearly 0, 0 also lies inside U. So this is satisfied. How about inverse? So inverse of, you can check, inverse of x comma x is just minus x minus. Why? Because x x plus minus x minus x gives you x minus x, x minus x. And what is this? 0, 0. Inverse of x is minus x minus. Okay, so this is a vector space. U is a subspace of V. Okay, that is U is a vector space which is sitting inside V. Can we represent it geometrically? What does U represent geometrically? So R2 represents the plane. R2 is the plane, that two-dimensional plane, right? And what is U? Well, U is points of this form, XX, that is XX type of points. But this represents a line, right? This line y equal to x. So this is x and this is y, and y is equal to x. So we get this line, y equal to x. This line represents U, right? So similarly, if I take this line, say this line, that will also give me a vector space, a subspace of R2. So say U1, or let's call it UM, x and x is a subspace of R2, right? So this gives you a subspace of R2. What is UM? Well, UM is nothing but the line y equal to mx. Okay. So every line that passes through origin gives you a subspace of R2. If you take a line which doesn't pass through the origin, let's say this line, then this lacks identity in it. It doesn't have the identity. What is identity? 0, comma 0. And it doesn't have 0, comma 0 on it. And therefore it is not a vector space. So it's not a subspace of R2. Okay. So we can say that R2 has three types of subspaces. One is the empty set, or not the empty set, the zero set. The zero set. Zero set is a vector space, right? It's the subspace of R2. Can you verify that? Okay, so verify it. Verify it at your home. Second is all lines passing through the origin. And third is R2 itself. Well, R2 is a subset of itself. and R2 is a vector space, so R2 is a vector space, right? So there are three types of subspaces: the zero set, and all lines passing through origin, and R2. Okay, now let's take a look at some more examples. Say A is the set of all continuous functions from closed interval 0, 1 R. And operations are, what are the operations? Usual addition. And here we're taking k equal to R. K equal to R. And usual scalar multiplication. Is a vector space over R? So if you take f and g, two functions on A, then f plus g is defined, right? If f and g are continuous functions, then f plus g is continuous as well, because sum of two continuous functions is continuous. Okay, so the binary operation makes sense. So f plus g is also inside it, right? That is, plus is taking elements from A cross A to A using the simple addition. So we have binary operation, fine. So the usual addition works as binary operation just fine. And we have scalar multiplication, so you can verify that it is a vector space, right? So it's a vector space. You can verify all the criteria for vector space. And let's take another example. Say P2. P2 is the set of all polynomials with degree less or equal to 2. And usual addition and scalar multiplication, and k is being taken as R. So you can see that P2 is also a vector space. Now look at this set. Say P1. It's the set of all polynomials with degree less or equal to 1. You can see that P1 is a subspace of, okay. So that's it for this video. We'll be meeting in the next video where we'll be talking about linear independence and linear dependence of vectors and some other things. I hope you enjoyed today's video and you understood and learned a lot of things today about linear algebra. Thank you for watching this video. Please like, share, and subscribe. Thanks and bye bye.